Thank you very much for your introduction. My name is Yuma Kawamoto, and I'm an industrial PhD student at Leapwave Technologies. Today, I'm going to be talking about the progress that I made on my thesis titled Ultra Broadband Wireless Communication Systems Development under the supervision of Alejandro Rivera Lavado and Guillermo Carpintero. Here is the outline, and first of all, let me briefly introduce our company, Leapwave Technologies. And then I'll talk about the motivation for my thesis and what I have done so far. And finally, I'll conclude my talk with future work. So Leapwave Technology is a spin-off company from UC3M. And we are working to bring a paradigm shift in high-speed interconnects using dielectric waveguides. We are offering a new technology, especially suited for high frequencies, and it can be applied to wireless communications, spectroscopy sensing, high-speed data links, non-destructive testing, and more. So let's move on to the motivation for my thesis, which comes down to a question: why do we care about high frequencies? So here is a view of frequency allocation, which is regulated by international bodies. And this frequency band up to 7.2 gigahertz, we are currently using this frequency band mostly. And these frequency bands up to 90 gigahertz are allocated for 5G networks. However, for 6G, we are expected to move beyond 100 gigahertz due to the increasing demand for high data capacity. So why do we need to move beyond 100 gigahertz? This is because in higher frequencies, there is a huge spectrum available which allows for high-capacity data transmission. One of the biggest challenges in using high frequencies is the limitation of existing interconnection technologies, such as coaxial cables, connectors, and rectangular waveguides. Coaxial cables and connectors can support a wide bandwidth, for example, from DC to up to 220 gigahertz. However, they suffer from high loss at high frequencies. On the other hand, rectangular waveguides offer low loss at high frequencies, but they're bulky and they provide limited bandwidth, as shown here by split bands. The solution that we offer to this challenge is to use silicon dielectric waveguides as a new interconnection technology. These waveguides can be easily fabricated by the standard etching process at very low cost. And they offer extremely low loss and broad bandwidth, and they are also versatile for developing functional devices. And the core structure of state-of-the-art technology from Leapwave, it looks like this. So it combines silicon waveguides, shown in purple here, with metallic transmission lines shown in yellow here. And with this technology, we can realize an ultra broadband system operating from 50 to 500 gigahertz. Here are the milestones of my PhD thesis, beginning with the development of transmitters and receivers based on silicon waveguides. And then I'll focus on building communication systems with the final goal of demonstrating high-speed data links. From here, I'll talk about the progress that I've made over the past year. As you saw in the milestones, I have mainly been focusing on the development of ultra-broadband transmitter, which is based on a photodiode called Uni-Traveling Carrier Photodiode, UTCPD. So the UTCPD is a high-speed photodiode that can operate at more than 500 gigahertz. And this UTCPD is fabricated on silicon carbide substrate, like this. And this is because silicon carbide substrate offers high thermal conductivity, which helps heat dissipation and improves the performance. This chip was then integrated with silicon waveguide, as shown here, with tapered slot antenna, which is metallic transmission lines. And this design achieves efficient coupling between a tapered slot antenna and silicon waveguide. Here are the simulation results. S11 represents the reflection, and S21 shows the transmission. And to evaluate the performance of the device, we typically use minus 3 dB as a reference for S21, which is a 50% power loss. So as you can see, this design achieves high frequency operation beyond 350 gigahertz. And these are the images of simulated electric field distributions at 100 gigahertz, 300 gigahertz, and 500 gigahertz. And most of the power is transferred from the chip to a silicon waveguide. We successfully packaged this device in this aluminum case and characterized it with this setup. We inject two-tone optical signals to the photodiode so that the photodiode can generate a frequency that corresponds to the frequency difference between the two optical tones. And as a result, we obtained output signals over 500 gigahertz in one single interface. If this is packaged with a rectangular waveguide, for example, we couldn't have achieved this broadband operation. It would look like this, something like this. Furthermore, we performed communication experiments comparing our device with a commercially available photodiode. Here's the experimental setup, and we didn't test wireless. We didn't do wireless test this time. Rather, we did back-to-back experiments. So we placed a photodiode here. We connected to the packaged silicon straight waveguide, and followed by silicon waveguide to a rectangular waveguide transition. This is a rectangular waveguide and a rectangular waveguide-based receiver. And then we conducted communication experiments at 110 gigahertz with on-off keying scheme. We typically look at the the eye diagram and bit error rate to evaluate the communication performance. And the eye diagram of on-off keying looks like this. So with on-off keying, the signals will be binary digits 1 and 0. And this is a time domain signal. So it's 1, 0, 1, 0, like on, off, on, off. So this is on-off keying scheme. And this eye diagram should be clearly open for successful transmission. However, in our case, we observed ringing here and here at 1 gigabit per second, which means we didn't achieve 1 gigabit per second transmission. And we found out that there are some resonances in frequency response of the system, which is likely to cause this ringing. So the potential causes of this ringing include the resonance caused by the bias and ESD protection circuit, which is connected to the device through metallic lines, and or the resonance in the device itself due to the metallic transmission lines being terminated open as an open structure here. So as for solutions, I will run some simulations at lower frequencies to better understand the electromagnetic behaviors. And then we could introduce a high inductance coil here and here to electrically isolate the device from the ESD protection circuit. If this doesn't work, the issue can be in this TSA structure. So we could introduce a damping resistor at the end of the metallic transmission line to suppress the reflection here and ringing. Here are the conclusions. So we developed an ultra broadband transmitter based on photodiode operating at more than 500 gigahertz. And we conducted communication experiments, but we observed signal distortion as a result. And the potential cause of the signal distortion is the resonance in the internal structure of the device. So for future work, I will investigate and rework the structure to suppress the resonance and try complex modulation and communication experiments to achieve higher data rates. And I will also work on developing a broadband receiver based on silicon waveguides. As a parallel line of research, I also worked on semiconductor near-field imaging using silicon waveguide sensors, and taking advantage of sensors' broad bandwidth, I analyzed the spectra of reflected signals from different materials on silicon wafer and applied the signals processing techniques and finally classified the materials. And this work was published in the IEEE Sensor Journal this April. So here are the research activities. I participated in photonics packaging course in Ireland, published a conference paper and journal paper, and I also contributed to the development of LeapWave's intellectual property strategy. Thank you very much for your attention, and I'll be happy to take any questions.